finding process capacity and bottleneck in a single product type case. We have considered the Circored plant process or facility. We have created a process flow diagram, and now we would like to analyze this process and find out what its capacity is and what is the bottleneck. So the bottleneck is defined as the resource that is limiting process capacity. It's the reason why we are not able to produce more than a certain number of units per unit of time. Process capacity, we defined it before as the maximum possible flow rate. In other words, it's how many units a process can produce per unit of time. And of course, flow rate is how many units a process actually produces per unit of time, right, given all the circumstances or the constraints. For linear processes, as is the case in the Circored plan, where, if you recall, the process had 7 steps, right? Each of those steps must be visited, or is one resource or several resources that must, and then all units must visit all those resources in order to become finished goods. The capacity of the process can be calculated as minimum of capacities of each of the resource. And when we do this, we can define the bottleneck as the resource with the minimum capacity, right? One of those CI is the minimum value, and the corresponding resource I is the bottleneck. So process capacity will be actually equal to the capacity of the bottleneck. And then we will also say that the flow rate should be either equal to available input, or right, also expressed as a rate of number of units of the product per unit of time, what we receive, or it will be equal to the capacity, or it will be equal to the demand, when, right, and whichever is minimum, this is what the flow rate should be. So the process, we say, is either demand constrained. When demand is the minimum, the process is demand constrained. If the other two elements are one of them is the minimum, then the process is supply constrained. And of course, if C is the minimum, then the process, we call it capacity constraint. And if the input is the minimum, the process is called input constraint. So when the process is capacity constrained, of course, the flow rate R will be equal to the bottleneck's capacity. To understand this better, here is a picture that shows visually what we mean by a bottleneck. So here, the distance, right, let's say from this point to this point, is visually trying to show you the capacity of one of the process steps. So here we have much more capacity, here we have a bit less capacity, here we have the smallest capacity. And because, right, this is like a neck in a bottle, this is the narrowest part of our process, and this is what is limiting the flow through the system, right? And also you see the size of the input is bigger, so we have enough input, but this step has the narrowest part, and this is why the flow rate is this wide. Notice that the demand here is very high and much higher, much larger than right, than the capacity of the step. Recall that all these measures are rates. So input is the rate at which we can get input in some units of the product per unit of time. The capacity of each of those steps, including the bottleneck, is number of units we can process per unit of time. And the demand is the number of units that we can sell per unit of time. This is a similar picture. However, here the demand is much narrower, right? Much smaller. So because of the demand, this process now is demand constrained. This was supply constrained, specifically constrained by capacity, and here it's demand constrained. And you might argue that even if demand is small like this, we should produce at a higher rate. I warn you that in general, it is not a good idea, because it doesn't make sense to produce more than you can sell. If you don't have demand for the product, if you produce more than the demand, you are going to just create a buildup of inventory. In some cases, when you have a good reason to believe demand will be much higher in the future, this might be a good idea. But in general, you should be very careful not to maximize utilization and produce, right, only what is demanded by your customers, because you might have a very large overproduction might lead to a very high buildup of stock, that eventually you might not be able to sell. Let us now go back to the case of the Circored plant and its process capacity. So suppose we talked to engineers and we found out that these are some facts about the 7 activities or 7 resources that are performing activities right in our process flow diagram. So some of the information is quite straightforward. The preheater can process 120 tons per hour, lock hopper 110, flash heater 135, discharge 118 per hour. So capacities of those steps are quite easy. But the first reactor, we learned the following. The first reactor, you can load it with 28 tons, and each 28 tons has to spend there 15 minutes. And let's assume the 15 minutes also includes the time of loading and unloading and anything that needs to be done before the next loading, right? So how would you calculate capacity? Well, we would calculate it as 28 tons divided by 15 minutes, right? This is units of product per units of time. Now I want you to see that 15 minutes is in fact 15 over 60, right? A minute is 1/60th of an hour. So I can rewrite it as 15 over 60 an hour. And of course, dividing by 15 over 60 is like multiplying by 60 over 15, or you could replace this, right? Simplify it as 1/4, right? 1/4 of an hour, right? So this is like 28 multiplied by 4 tons per hour. So 28 times 4 is 112 tons per hour, right? So we've determined process capacity, step 3 capacity, right? And then we have the second reactor, a similar situation. Sorry, you can load it with 400 tons of iron ore, and this needs to be processed for 4 hours. Again, assume including loading and loading time, right? So again, we can say 400 tons per 4 hours, right? Which is equal to, this is easy, 100 tons per hour, right? And the final step, there are 3 briquetting machines, and each of them can process 55 tons per hour. So like we have 55 tons per hour, but each of them can work in parallel. That means we have 3 times 55 tons per hour. So we can say this is 165 tons per hour. And I hope you see there is some, there are some differences, right? The capacities can be as high as 165 tons per hour, 135 here, right? These are quite high. The lowest of them is this one, 100 tons per hour is the smallest that we get, right? Let me highlight this. So if you try to find process capacity, right? Recall this is the minimum of C1 to C7 in this case, right? The minimum, and that is 100 tons per hour, as we already highlighted, right? And we can also say that the bottleneck is the resource that had the smallest capacity. C4 was the smallest, so the bottleneck is the second reactor, right? And notice that its capacity is equal to process capacity, right? So we have found the bottleneck and the process capacity for the Circored plant case.